So hold on 1 second. All right. So last class we started talking about frequency estimation, where you're given a stream, you process the stream, and at the end of the stream someone asks you a query, and we have to answer that query in this form of, okay, what's the frequency of this item in the stream, what's the fraction of times that the elements you see was this particular one. And we were okay with estimates. If you wanted exact counts, we needed a lot of memory, so we were okay with estimates, but we wanted to use less space. So we saw the a deterministic algorithm, the Mr. Grease algorithm, which had one very good guarantee, which has some very nice guarantees. But then we wanted something broader, right? So we wanted the sketches, a linear sketch, which allowed us to combine statistics of streams, right? So now to that we introduced this count sketch, which gave us some estimate. And today what we'll do is to refine count sketch to get one of the most used frequency estimation algorithms, which is count min sketch. And then we'll talk about an advanced problem in frequency estimation. Okay? So what was the count sketch, right? So we first fixed a random hash function from the space of items to some k, where k is a parameter. And we also introduced some counts, c1, c2 up to ck. And the idea was that each count would keep track of all the items that have been hashed to that particular bucket. Right? So whenever we see an item x, we increase the corresponding counter from the hash of x by 1. Okay? And upon a query, we just return the count divided by the number of items n. And we saw that the estimate that the algorithm returns is always at least the actual frequency, and at most the actual frequency plus 1 over k. And then, an expectation is doing pretty well. The estimate is close. If I choose k to be something like 1 over epsilon, then my estimate is only epsilon far away. But we wanted to understand the reliability. And the reliability was somewhat okay, right? So the probability that you're more than 2 over k away is at most a half. Okay, so that's good. But now let's try to see if we can improve this half, right? Particular, let's say I want reliability, which is like 99%. So I want my estimate to be not too far most of the time, not just 50% probability, but most of the time. How can I do that? How can I get a better estimate on the actual frequency with more reliability? Any suggestions? So we have one estimator here. So if I want to boost reliability, what's a common trick that we use? Right, so I have one estimator which gave us some reliability, and if I want to increase my chances of being close to being correct, one trick that I can do is
use multiple estimators.
Right, so I can use multiple estimators. So that here would correspond to using multiple hash functions, right? So let us boost reliability. Okay, so boosting reliability would mean I use multiple hash functions, right? Each estimator is one hash function. So this is what count min of S is a parameter which controls how many estimators I'm going to use. Okay, so I first pick hash function h1, hash function h2, hash function hs. Each of them are randomly chosen. They're completely independent of each other. So random, independent. Right, so it's a bit like, you can use different dictionaries or something like that on any programming language. Okay, and we will have a counter, k counters for each of the hash functions, right? So basically we'll have Cij is 0 for 1 less than equal to I less than equal to S and 1 less than equal to J less than equal to K. Right, so earlier we just had one counter. Right, so this is C11, C12. Okay, instead of just keeping k counters, now we have k times s counters, k counters for each hash function. Okay, and then for each element x in the stream, what can I do? What should I do? Right, so we're just running the algorithm s times separately, right? So what we need to do is pretty simple. We just have another for loop for each of these counters. Right? So basically if x, for example, comes up and it's hashed, let's say, to this element under the first hash function, this element here under the second hash function, and to here, we increase all those counters. So every element will lead us to increase k entries in this table, and they're kind of chosen randomly everywhere. Right? That makes sense? Okay. So this is the part of the algorithm that processes the stream. Okay, so that much is kind of fine. But how about the query phase? So what should I return when I see a query? So earlier, we just went to the corresponding counter C of h of a and returned that. But now we have S things. So what should I do? Any suggestions? So imagine, A comes and maybe it's hashed to here, 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 and maybe somewhere here like this. So which of these cells should I return? Exactly, return the minimum, right? Because we know that every one of them is an overestimator. You're never doing an underestimate. Every one of them is an overestimator. So taking the least one is the closest to the true answer, right? So that's exactly what count min sketch is. I mean, there's a min inside the title of the algorithm because we're going to return queries, answer queries by looking at the minimum of all of these k cells in the table, right? So query, you returned min of sorry, this should be an S. And there's a 1 over n just because we're looking at the fraction and not the actual count. Okay? Does this make sense? And it's a simple trick, like, I mean, it's kind of a natural thing. We know you're overestimating every time, so just take the minimum. Any questions? Okay. So this is a different algorithm now. So it takes a lot more space. It takes k times s amount of space, as much, compared to just count sketch 1. But what does it buy us? How does it performance improve? And the reason we do this is that it gives us a very significant boost in the reliability. Okay, so the claim this is our new estimator f tilde a, right? Okay, let me put double tilde just in case you're not confused with the earlier one. And we can show, just as before, that this is still an overestimator. You're taking a min of a bunch of overestimators, right? So it'll still be an overestimator, but perhaps a bit better. And what can you tell me about the expectation of this new estimator? Is it close to the old one or no? What do you think?
It's less than or equal to the old one?
Yes, because you're taking a minimum of a bunch of random variables. So its expectation can be at most the expectation of any one of them, which was this much. Okay? So we are good, like, the expectation is good and we are always lower bounded, so this is fine. But we didn't improve much in the expectation. Right? So what hasn't, this hasn't changed much from what we had when we didn't take the minimum. Okay? But what changes is the reliability. Right? So I want to look at the probability that my estimate is more than 2 over k. Right? So the estimator we saw in the last class had, somewhat of a mixed bag in terms of reliability. It was a mixed bag in terms of reliability. The probability that you're 2 over k away was 50%. That's the best we could do. But how about now? What do you think this is? Any guesses?
I feel like this is like like exponentially small in the number of repetitions.
Exactly. Right? So which is great, by taking S copies, we are getting an exponential boost in the reliability. And why do you think this is? Like, what's the reason to expect such a thing?
So like if this happens, if f double tilde is larger than 2 over k, that means that every single one of the S estimates was larger than 2 over k. And that happens with probability a half, and they're all independent. So
Exactly, right? So we're taking the minimum. So
yeah.
for this bad event to happen, every one of our hash functions should do badly, right? So it's not just enough for like one guy to badly, but every one of them should do badly. Like even if one was somewhat good, the minimum estimator would be even good, right? So the reason is that if right, so every one of them must be bigger because we're taking the minimum. If the minimum was bigger, then every one of them was individually bigger, right? And these are all independent, and each one happens with probability half, right? So we could get unlucky and be wrong on the first hash function with probability half. But what's the probability that you're unlucky every one of those s times? That has to be exponentially smaller, right? So probability that this is equal to probability for all I 1 through s, we have this okay, but these are all independent, so we get this is most 1 over 2 to the s. Okay, any questions? So this is great in the sense that if I wanted reliability, which is like let's say 0.01, then I just need to repeat my algorithm maybe 10 times or 20 times, and that's all I need, right? I think that's even more pessimistic. You just need to repeat it a few times. If I repeat it 10 times, my reliability is almost like 0.001, 1 over 2 to the 10, right? Okay, so summary S copies gives us okay, and so so let's do a quick summary of frequency estimation. Right, so we saw two algorithms. One was Mr. Agrees. Okay, so there the space was O of k times log m plus log n, and the error was 1 over k. So in a sense, if I flip the quantifiers, let me write it maybe with a different color. So if I wanted error epsilon, then I need space, which is log m plus log n divided by epsilon. Okay. So remember we introduced this epsilon comma delta estimator, and this is like a deterministic estimator which is always within epsilon of the true answer, right? But the downside of this was that it wasn't a sketch. We couldn't combine multiple streams in an easy way. So just apples to apples, this will beat continent sketch, but it doesn't help us combine streams, which is a very important property when you deal with big databases. Right? So in fact, what gets used more often is the complement sketch. And that is what is deployed on most routers and things like that. Complement sketch also has a very interesting history. It was developed at AT&T with the explicit purpose of being used on their switching networks. So the space is, for each one it's similar, but then we also do S copies. Right? Okay. So if I wanted epsilon comma delta, probably approximately correct estimate. So remember we said, it's a epsilon comma delta probably approximately correct estimator. If my answer is epsilon close with probability at least 1 minus delta, then I need space which is okay. Any questions about this? Okay, so that's all I wanted to say about frequency estimation, where we are trying to solve this specific problem. But now let's try and talk about other streaming algorithms, specifically those where in the end you're maybe not interested in not like a single item's frequency, but some overall statistics of the stream, right? So for example, you just keep getting your Facebook, you're getting IP address, pings from different IP addresses, right? What if I want to count the number of unique visitors to my website? How can I do that? What if I want to find out, what's the distribution of the visitors? Is it just one country which is highly dominant in terms of the number of visitors versus another country, or things like that? Okay. So I want to infer properties of the counts of each element in the stream. So, let us start with just the okay. So I keep seeing this stream and I need an estimate of the number of distinct elements in the stream. How can I do that? We'll solve this problem, and along the way we'll also see this very important idea in randomized algorithms where it's a slight twist on how you can boost reliability by taking a slightly more nuanced look than just taking multiple samples. Okay, so let's take a 5-minute break, and when we come back, we'll try and answer these questions. In the meantime, think about it a little bit and let me know if you have any ideas. So we'll resume at 10:35. I mean, you can think of a number of applications for the ability to count the number of distinct elements, right? If you're a database, then keeping track of this could help you decide on all kinds of things like, okay, when should I double my allocated space? When should I partition my database? And if you're a website, it keeps track of statistics like what's my head count, what's my unique visitor hit count, and things like that, right? And you want to do this in a fast way. You have to process each element very fast and also use very little space because again, the stream is never ending, right? So how can I do this? Any suggestions? Did anyone have any? Just think of what would you sort of try, for instance, if I ask you to count the number of distinct elements.
So, I mean, you have to somehow keep track of like the things you've seen so far so that you know when you've seen something new. So, I mean, I don't know. The naive thing to do would just be keep track of all the things you've seen so far in like a hash set.
Right, but then if you hash, the size of the dictionary is linear, right? So
Yeah.
it's not very efficient. You can build a dictionary for sure, and it will save you something in terms of the space because the space, instead of being O of m, it will be O of the number of distinct elements.
Mm-hmm.
The size of the dictionary is the number of distinct elements in the thing, so you are saving something there, but not enough. You can do much better. Okay, so here's a very clever solution. I think is due to Fajolet and wait, I should remember this. And Martin, FM. This is called the FM estimator, and let's look at what it does. So the basic idea, it's kind of a surprising thing that people use, and people have tried to use this for many other things later on, right? So okay, so let me ask a question. So suppose I have a set. Okay. So pick a random hash function edge from to the real numbers. Suppose I picked a random hash function from my space to real numbers. So basically, again, real numbers is just an overkill. You can do with all kinds of finite bit precision stuff. So, but let's not worry about that. So for each item, I'm just throwing out a real number, right? In some sense, if you think of this as a 0-1 interval, then I'm kind of picking out m random points here. They need not be uniformly spread. Some of them will be close to each other. Most of them will be kind of about some distance away from each other, right? So what do you expect in regards to the distance between items? Like, maybe about 1/m sort of makes sense. They're kind of spreading out evenly. But here's the deal. What do you expect the minimum of these items to be? Any guesses? If I throw one item, it can land anywhere on 0 to 1. If I throw two items, I expect one maybe on the left half, one on the right half, and things like that. Right? But what about the minimum? come on. What do you expect the minimum to be?
I'm trying to do the calculation in my head, but
We'll do the calculation, but just kind of a guess, right? If I throw three items, I pick 3 points on the interval 0, 1, you'd expect one of them to be in the first third, one to be in the second third, and one to be in the last third. You know, it's not rigorous, but you know, that's your expectation, right? And that's exactly what we are going to exploit, right? So the idea is that what is min of okay, it turns out that this is basically like 1 over m. Okay, and this kind of gives us a handle on how many distinct elements there are, right? So the FM sketch is the following. So you pick a random hash function h from 1 through m to 0, 1. Okay? Alright? And so if I go with this intuition that if I pick, you know, some m points, or actually let me not, right, if I pick s points on the interval at random, the minimum is going to be about 1 over s. Okay, so how can I use that to get some estimate of the number of distinct elements, right? So the hash function is fixed for each element right now, right? The hash value. Now, if I have many distinct things, we'd expect the minimum element among them to be small, right? So somehow if I have many distinct things, then you should go closer and closer to the origin. You should see at least 1 point close to the origin, right? So that's the estimator, which is x equals min of, you know, you start with x to be 0. Okay, let me not use x, let me say y.
so you don't even have to remember anything at all.
Nope.
That's so crazy.
Real number on the real line. Again, as I said, it's just finite precision. You don't have to store the real number. You just keep calculating this minimum.
That's crazy.
So basically, it's saying, you know, I have this. If I only see one item, if my entire stream is made up of only one item, then this entire process, what it's doing is picking one random point. If there are 10 items, then I'm picking 10 random points, right? And so on. Does it make sense? So that's the intuition. We'll see the analysis pretty soon, but that's the rough idea. Okay? So that's how you process the stream, and so the estimator we'll get to in a little bit is going to be basically 1 over y. Okay, so this is kind of, version 1.0. We'll refine this in a little bit. But why does this make sense? Right? Why is keeping track of the minimum a meaningful thing to do? Okay, and the idea, as I said, is following. So clean. So you can actually show that whatever we're computing, this minimum value, its expectation is exactly 1 over the number of distinct elements plus 1. Okay, and that's why we kind of, it's not really strictly speaking kosher to reverse these estimates, but that's why I said it's version 1.0, we'll revise it. But the idea is that if I keep computing this minimum, I'm just storing one real number for the entire stream. It doesn't even have to be a real number. Then its expectation gives you is correlated with the number of distinct elements.
Professor?
Yeah?
So in our algorithm, we initialize y at 0, but if we're calculating the minimum of y in h of x, won't that always be 0?
Sorry. Thank you. This should have been 1. Yeah, thank you.
Oh, okay.
Yeah. Good. Okay. So I'm not going to spend too much time on it, but the basic idea is that if I draw 3 points at random on the line 0 to 1, you expect one of them to be in the first third and so forth, right? And this is kind of, maybe, in fact, I think it's one of the favorite interview question where people will ask, if I draw 2 points in the unit line, what's the minimum, what's the expectation the minimum? It's 1/3. And it's exactly that statement. And the proof of this, you just write down some integral. I'm not going to prove it. This is not a class 1 integration. But basically, so what's the probability that y is less than some value? Suppose I'm interested in the probability that, actually let's do something like this. What's the probability that this minimum is more than some point on the line? What's the probability that the minimum is at least 1/3? What is the answer to that? So the PDF of this y, it's a continuous random variable, it's kind of weird. But what's the probability that it's at least 1/3? It's more than 1/3. Well, if it is to be more than 1/3, then all of the distinct elements in the stream must be mapped to the last 2/3. Right? So for example, if I put right? So this is my 1/3. Then each distinct element gives me a new point on the line, right? So that's where the distinctness is kind of really exploited. Repeating the same item again and again doesn't give you a new randomness. Only the first occurrence gives you the new randomness, right? So if I'm interested in the probability that the minimum is at least y, then all of those hashes, all of those random points should land here. And each one happens with probability 2/3, right? So for example, probability y is greater than equal to 1/3 is exactly 2/3 raised to the number of distinct elements. Okay? So if I let n0 equal number of distinct elements in stream, then this is exactly 1 minus y to the power n0. Okay? Alright? And if you know some calculus, you can show that the expectation of any random variable is integral of probability y is greater than or equal to y dy 0 to 1, and this is right. So this is just some way to calculate expectations of continuous random variables by integration. Okay, but the main thing is this fact that this probability depends on the number of distinct elements and not like the order of the stream or how many times each element repeats itself or anything like that. Okay, does it make sense? Okay, so definitely looking at y tells you something about n0, right? So in some sense, you're not getting an estimator for n0, the number of distinct elements, but you're getting an estimator for 1 over that, okay? And you could conceivably flip it to improve the accuracy, okay? Does it make sense? And to get a better handle on the estimator, what you really need to do is so once again, just as before, how can I improve the reliability? Well, I can take independent copies, right? That's my standard trick. So let's do that. So I can say pick independent hash functions h1 to hs from, oops, my arrow is different. Okay. And you instantiate k counters. Okay, so to improve the reliability, you can do the same trick as before, which is to run multiple copies, right? Make sense? And but now this one question, like what should you answer at the end? How do you combine these multiple copies? So earlier we were kind of always overestimating, so we said take the minimum. But now we could be overestimating, we could be underestimating, we could be doing all kinds of things. So what should we return in the end? The average, yes. So when there is no clear trend in which you know you're overestimating or underestimating, you should take the average. That's the most reliable thing to do, right? And then you output okay, but there is some subtlety here, right? So you're not returning the average of 1 over yi minus 1, but you're first computing the average of these y's and then doing the reciprocal and so on, okay? So there is this one subtlety to keep in mind. Does this make sense? Okay, any questions about that? Okay. So I want to end with one very useful trick about boosting reliability, right? So let's see what this buys us in terms of, what does it help us say about how good our estimator is, right? So far, all we know is that expectation of I is 1 over m0 plus 1. Okay? So when you take the average, it should still be true that we are good in expectation. In some sense, we're getting an estimator for 1 over the reciprocal roughly. Okay? But in such a case, if I want to get an estimate on the reliability, what other information do I need besides the expectation? Right, so what other information do you need besides the expectation?
Reliability. Like,
The probability, but that's too much information. That's often very hard to compute. So often, along with the expectation, if you have an estimate of the variance, then you have you can estimate the reliability reliably, right? So smaller the variance, the better your estimator is. Okay? Like somehow, if you're varying all over the place, but you're still correcting expectation, that's less meaningful than you kind of concentrate in a small interval. Variance is small and you're good in expectation. Okay? So how can I address that? So the variance of y. Okay. You can do another calculation of integration. We have the exact formula for the distribution, right? It satisfies this equation. Okay. And you can do some calculus to compute the variance, and it comes out to be about 2 over n0 plus 1 whole square. Okay. So in other words, so the expectation of y is 1 over n0 plus 1, and the standard deviation is at most square root 2 over n0 plus 1. Okay? So meaning the variance is, the standard deviation is roughly of the same magnitude as the expectation. which is not very good by itself, right? Because if my variance, so somehow you should think of standard deviation as giving you the width of the interval around which your random variable lies, roughly speaking, right? So it's saying, okay, my expectation is something like 1 over n0 plus 1, and this is 0. But my standard deviation is pretty big, like, it's covers this region. It's bigger than my expectation, so it even includes 0, which is sort of seems pretty bad, right? So this by itself is not a reliable estimator, but that's why we were averaging. Okay. So this is the variance of a single copy, right? And so what's the variance when you average multiple copies? And this is something that you did in one of the homework problems, where if I have a single estimator, then it has some variance, but if I average multiple ones, then my variance decreases, right? And if you go back to that calculation and check, you'll get the variance is exactly this much. Okay. If I average S independent copies, then the variance decreases by a factor of S for any random variable. So this is at most 2 to the S times n0 plus 1 whole square. Okay. So now we are doing better, right? So now the standard deviation of y bar is at most okay. So we improved the standard deviation. So now if I take S to be sufficiently big, then maybe my standard deviation will be sufficiently small so that I get a tiny interval around my expectation. Okay. Final question. If I know the variance and expectation of a random variable, what tool can I use to get an estimate on the reliability? Any guesses? So there is this thing called so I know the variance, I know the standard deviation, but this still doesn't answer the question, when is this far?
Well, you can use z-score.
Can you say that again?
You can use z-score.
I can use what?
Z-score.
Yes. Okay, so how can I get an estimate on the reliability? We can use this tool called Chebyshev's inequality. Okay, which is a very widely applicable thing and says that for any random variable y, the probability that you deviate from your expectation by an amount of t is at most the standard deviation of y divided by t. Okay? Makes sense? Is at most, in fact, it's a square of this guy. Right, so let me write it slightly differently. Is the variance of y divided by t squared. Yeah, I think that's the best way to write it. So if I have an if I know the expectation and the variance, then it gives me some control on how far am I going to land from the expectation. Like, in this window around the expectation, what's my distribution like? The farther out from the expectation I am, the smaller the probability. Okay? So if I use that for our thing, then so we know the variance was 2 over S0 times N0 plus 1 whole squared, sorry, not S0 but S. And then I'm applying with T, which is like an epsilon factor multiplicative approximation. Okay, so this is okay. So it's basically saying, like, if I want a 0.1 or 1.1 factor approximation to N0, then I need to choose S to be something bigger than 1 over epsilon squared, 1 over 0.1 squared, to get some reliable estimate. Okay, does this make sense? Yes, no? Right? Okay, so summary. Okay, so if you want something within a 1 plus epsilon factor, like 1.1 factor, I need, and with some reliability, then I need to take S to be correspondingly high, right? So for example, to get epsilon comma delta estimator, so if I need to take, I want to make this probability to be at most delta, then I need S to be something like, okay? Right? So if I just take multiple independent copies and average them, then I can get a pretty good estimator with good reliability. It's amazing, right? So, and what's the total space? The total space is log n. So it really is just log m. I just need to store this minimum value, right? And that's within log m precision. So it's just this divided by S times log n, which is something like and the constants are also very small. It's just like 2 log m over delta times epsilon squared, which is amazing. Okay? Right? So, I mean, this is an algorithm that actually gets used in all kinds of databases where they just want like some kind of crude estimator, to decide when to kind of duplicate a dictionary or when to sort of do all kinds of things. This is well and good, but there's still like, some annoying thing here, right? Which is, how does this compare to count min sketch? There we were able to get the estimates of individual frequencies, right? But in terms of space, the dependence on reliability was basically exponentially better there, right? If I wanted delta reliability, meaning my probability that my estimator was far off was at most delta, then the dependence was log 1 over delta. But here it is 1 over delta. So if I want reliability, which is like 0.001, then I need to use 1,000 times more space, which is really, it's kind of defeating the purpose almost of using this entire approach in the first place. Right? So what can I do then? Any suggestions, ideas? How can I get better estimate on the reliability? All right. So this is the trick that I wanted to tell you about. This is not specific to streaming algorithms. I hope it's kind of, a trick that you can use whenever you have randomized algorithm for which you want to improve the reliability. Okay? So boosting reliability beyond independence. Okay. So suppose I want to calculate so which is a better indicator of the actual sample, the median or the mean? What do you think?
Median.
Median. Why?
Because, well, it's taken from the actual samples, like it's not like calculated using.
Right. I mean, that's true, but there's also kind of a more precise reason why. Because
I mean, it's also less susceptible to outliers and stuff.
exactly, right. It's less susceptible to outliers. Imagine I'm trying to collect some information by some crowd poll or whatever, right? But there will be some people who just give completely random answers, right? So let's say I'm trying to calculate average salary of a bunch of people by just like, let's say questionnaires. Everyone will say, okay, their actual salary is so and so, maybe it's $100, right? Whatever. Okay, 100, 101, 150, something like that. And then some person who just wants to spoil our questionnaire says, okay, salary is $1 million. Then the average is completely distorted by this one number, right? By this one outlier. And here's where median is a better indicator, right? So if I take the median, it's kind of still dictated by what's happening in most of the samples and not just by one outlier, which can distort my answers completely, right? So if you are ever interested in purchasing houses, you should look for the median house price and not the mean house price, the average house price. That can be distorted if you're living in, anywhere close to UCLA, for example, right? So how can you bring that intuition into into what we are doing? Any ideas? How can I use the median? All right. So Median is more reliable. What is even better is median of means. Okay? So this is called median of means, you know, trick. So let me say it's a trick. It's really, I think, more than a trick. It gets used a lot and it's very valuable. But let me just call it a trick. Okay? So what you do is, suppose I have one random variable. Okay? Y. If I can get independent copies of it, right, and I want to boost my estimate reliability, I can just take average, which gives us some boost. Okay, but if I take the median, it also does something better. But the best thing is as follows: I take S2 copies. So let me write it. Y, a random variable, we want to estimate expectation of y. Hold on, okay. We said, taking independent copies, approach 1, take independent copies. Okay, so this is something that we just saw and maybe something that you've seen before and used before. Okay, so the M and M approach is I take number of independent copies, but I kind of group them into batches. Okay, so I take y11, y12, y1s, let me not write there. Okay, but then I also take more independent copies. Right? So I'm taking a bunch of independent copies as before, but I'm grouping them into sub batches. Okay? And then I compute the average across the rows to get some boost in the reliability. Okay? And then after doing all of this, if I just take the average again, then it's just, I'm computing the average of the whole set of numbers. I haven't changed anything, right? But now the trick is to do to take the median of these means. Okay? All right? Does this make sense? So the intuition is that somehow, suppose I tell you that your average is good with probability 3/4. Your first row has some reliability. It's giving you an approximately good answer with probability 3/4. So you're wrong 1/4 of the time, right? And then you have multiple things here. Taking the median now helps you boost it, because if the median is wrong, then most of them should be wrong. Right? So just as for count-min sketch, we said if your final estimator was wrong, every one of them had to be wrong. Here it's something similar. Like, if the median is wrong, most of them should be wrong, and each one is wrong only with probability 1/4. Okay? So you can actually show, that's a median-of-means trick. It gets used a lot. And the claim is that, let's say y is a random variable. The expectation of y is some number mu. It doesn't matter what it is. The variance of y is the variance is roughly the square of the expectation, which is what we had, right? Our estimator for the number of distinct elements had this property. The variance was at most 2 times the square of the expectation. Okay, think of C as a small constant, 2, 3, or whatever. Okay, let's call this guy as y. Then the median of means estimator Okay, so let me state a more condensed version. Okay, so you only need to take log 1 over delta copies. You'd only need to take log 1 over delta averages and then take the mean. Right, so you're getting a boost, a significant boost here. Your dependence on the reliability is again logarithmic instead of being 1 over delta. Right? So if I take delta to be 0.001, then once again I only need very few independent copies. This is a general statement. It applies for almost any random variable. Okay? Does this make sense?
Professor, so just making sure I understand this. So for this algorithm, you're going to have S times L hash functions?
Mm-hmm.
Okay.
Right. So this is the generic statement for any random variable. Now, if we go back to so what we'll do is pick hash functions h I comma j from okay. So for L is log 1 over delta roughly, S is some constant over epsilon squared. Okay, so L is O of log 1 over delta, S is O of 1 over epsilon squared. Okay, and then for each item x in the stream, for each I comma j, let's say, okay, so you're basically storing a table, like a matrix, right, with L rows and S columns, and each one is an independent copy of the previous estimator that we had. All right, and output. So that's how you process the stream. In the end, if someone comes and asks, okay, what's the number of distinct elements, you compute y bar I is right? You compute the row averages and then compute the median. Okay. So this is how you process the stream, and in the end, when someone comes and asks you the query, okay, tell me what's the number of distinct elements, I do this compute the means and compute the median. Okay, and you can keep track of the means continuously and compute the median on the fly as needed if you want. Does this make sense? Okay, and if I call this guy okay, so if you wanted something which is good within 1%, right? That is epsilon is 0.01, then it set epsilon to be 0.01, and then reliability is delta, then I would set L to be log 1 over delta. Okay, maybe this notation is confusing, so let me expand on that. Probability that answer minus n0 is greater than or equal to epsilon times n0 is at most delta. Okay, so that's what we get. That you're getting a very good estimator with errors like 0.01. Reliability can be boosted exponentially. Okay, any questions about this? So there's a question, how does the mean of median random variable guarantee change if we set L equals 1 or S equals 1? So if I take the mean of everything, then I just get back the guarantee of Chebyshev's inequality, right? So instead of getting, so here somehow basically the reliability is exponential in L, okay? Whereas if I just took L to be 1 and mean of everything, then I just get reliability which is something like 1 over L and nothing else. Okay? And if I don't do the mean and just took the median overall, then you'd still be getting something linear like 1 over L and not much better, right? And the intuition, really the reason we can do, we're gaining something is that the initial averaging over the rows gives us reliability which is like maybe 3/4. It says that probability that you're wrong is like 1/4. As long as you can push it down below 1/4, taking the median will help, right? So if your answer is only correct 50% of the time, then taking the median is not going to help, right? Because the median could be the wrong answer. But once you kind of cross this threshold of half, if most of these rows are good, then taking the median will help. Does that answer your question? Like, once basically you take S so that you get slightly below half in reliability, and once you get slightly below half, taking the median will boost it. Okay? Yeah, so that's the reason, that's a very good question though. Yeah. Anything else about this? And you can use this Medain-of-Means all over the place, like it's not specific to this random variable, and in fact it gets used for all kinds of things. Okay, so let's summarize. So we saw how to compute we can count with only log n bits of memory. That's the first streaming algorithm we saw. We can estimate frequencies with only logarithmic memory. We can count number of distinct elements with only logarithmic memory. Of all of this, the distinct elements one I find is somehow the most clever, because taking the hash and then the min is a pretty nice thing to do, right? Kind of gets around all these issues in a very beautiful way. And streaming algorithms, you can teach a whole semester, like a quarter-long course, right? So the next steps are what are called frequency moments. You can compute It's not clear maybe right now why you'd be interested in something like this, like, sum of squares of the counts. But this tells you about some distortions in the statistics, and people in database are scared about it, and they developed algorithms for computing these things in a space efficient manner too. Right? You can solve all kinds of linear algebra questions space efficiently. You can do principal component analysis space efficiently when the points are coming in on a stream. Okay, so basically all the learning problems, many of them, you can ask in the streaming setting too. Okay, so that's all I wanted to say about streaming algorithms. And so what else? And so we had 5. So just for the overall looking at the course, we looked at 5 different sort of topics, right? One was optimization. Gradient descent, stochastic gradient descent, accelerated gradient descent. Okay, these are really the workhorses of machine learning, right? And as I said, you can use these algorithms without knowing anything. Like, you install TensorFlow, you can just call it to train using gradient descent, stochastic, Adam, Nestor, all kinds of things. But it's good to understand when they work and when they don't work, because you might have to tune them to your applications and develop kind of new things when they don't work. Okay, and that's what we did. We kind of rigorously understood when these things work and when these don't. And the second topic we saw was online learning and multiplicative weights. So multiplicative weights again kind of shows up all over the place. You can think of it as multiplicative gradient descent. Whenever you're optimizing on the simplex, things where sparsity is important, I think it's a very natural thing to try as a first step. Okay, and there are many questions in statistics where that is indeed very important. And even in deep learning, it kind of shows up in many places. The third thing we saw was principal component analysis. And here you're kind of trying to find a succinct representation of the data set. And once you do that, the idea is that often it really helps in sort of getting rid of noise. And after that, you can do all kinds of supervised learning problems. Right? So PCA is an unsupervised learning problem. I'm just kind of give me a data set, I'm modifying it in some way. And after doing that, I do all kinds of supervised learning on top of that. Okay? That's something to keep in mind. And then we started looking at more specialized topics. I'd say the first 3 are sort of more generic techniques which are applicable broadly across learning theory and machine learning. And here we were talking about more specific learning goals. So we talked about learning graphical models, and this graphical models is probably one of the most underdeveloped things in the set of topics that we saw. There are very few rigorous guarantees. For instance, we don't know how to learn single layer Boltzmann machines, right? Which are very important in representation learning. Finally, look at streaming algorithms. Right, so streaming algorithms have less to do with learning per se, but more about scaling things to huge data sets. Right, you want to aggregate statistics. They are often used kind of in the back somewhere in trying to implement all kinds of ML systems and database systems. And all of them have tons of open questions, very close to what we saw. And we also saw some very recent results in this section. Okay? So that's all I wanted to say for this lecture. And I'll post the final on June 7th at 9 a.m. and you'll have a 24-hour window within which to start the exam. You'll have 3 hours after you start the exam, and it covers all the topics. And in terms of preparation, I'd say, just go through the homeworks, go through the main ideas, like the main algorithms, how they're useful, and what we know about them, and that should be the most important part. Okay? And because it's time limited, there won't be any programming in the final, it will just be theoretical. And that's it.
And it'll be on Gradescope.
It will be on Gradescope, yes.